Hey, welcome to Complex Numbers Part 5. This is a very busy screen here. Have a look, we're talking about, here we are, the geometry surrounding points on the plane. Okay, also known as, where could Z lie? Or, what is the locus of Z? The locus is from the Latin meaning place, and what we're saying here is we're trying to find where Z is placed on the plane, if you like. Like, what's the rules regarding Z if they are going to be possible positions, here we are, around that circle there? What would be a statement that would describe the locus of Z, where you would look for it if it was on a circle like that? Okay, so there's a few little diagrams here you might like to look at. Oh, y equals x. Looks like this might be a reflection in the line y equals x. So what we're going to do here with the complex number plane, the Argand diagram, is we're going to revisit some of the geometry, you know, from other places, even from the unit circle and the Cartesian plane, recalling some of that stuff. But my question for you now, there's a big question here. There are two errors on this page. Can you find them? Okay, there are two errors. Actually, the same error repeated. So you might pause the presentation, study the diagrams, and see what you think. All right, come on down now. Let's have a look at that issue and see what we've got here. Here are the two diagrams that have got a slight fold in them. Can you see it? Well, let's have a look over here at Z take I going in this direction. Is that correct? Looking at what? Sum of the vectors around a closed figure. Would you say that was correct? That direction for Z take I. Okay, let's check it out. Here we go. If we start looking at displacement of the origin, we displace it Z to here, and then we'd go Z take I, and then we'd go neg I. And that does not equal the zero vector. So what's going wrong there? Okay. Well, let's have a look. That Z take I, that's going to be sum of vectors around a closed figure is equal to 0, the zero vector. Then this Z take I should be up this way, shouldn't it? Should be in the opposite direction there, not that direction. And then we would be going opposite to it, so it'd be take Z take I, and then take I. And that then, if you look at it, would be Z take Z plus I take I would be the zero vector. Okay, so what about this one over here? What about the Z take 2? Is that actually going in the right direction? The same answer there, of course. It should be Z take 2 should be going up there. This is reasonably important later on, but at the moment we're just looking at the size of that, so not too bad that the text has got that wrong, but it's important to see that Z take 2 is a vector emanating from 2 and going to the end of Z, because we're going to use this for our locus problems quite a bit, because we're going to say, where do you look for Z? So we don't know this one in these problems. We might be given information about Z take 2. So we need to know that Z take 2 is emanating or starting at 2. And where it ends implies the position of Z, starting at 2. And if we have a condition on this, it will give the position of Z, which is unknown. So we don't really want to find Z take 2 coming from the end of Z, because we don't know where Z is. Okay, you'll see that coming up now. Okay, let's go down and have a look. And this is what I've got for you. So if we said the size of Z take I was 2, geometrically, what does that mean in geometry? Well, let's pull it apart. First of all, what's the size of Z? Well, that's its length. Or if you're starting from the origin, the distance from O. Okay, so what is the length of Z take I? Well, it is its length. Okay, we're not going to call this distance from O now. We're thinking about Z starting at the origin, and we're going to try and find it. So Z take I, the size of Z take I is 2. What could that possibly mean about a Z emanating from the origin? Well, this is the length of the vector Z take I. That's what that is, and it's saying, therefore, the length of the vector Z take I is 2. So we want all vectors Z such that the length Z take I is 2. Let's come down and look at it then. That's where we need this diagram here. Okay, just come up here a little bit. Okay, so if we don't know where Z is, we're pretending. We're saying, therefore, that Z take I has a length equal to 2. So let's start with I. There's I, the position of I is 0, 1. Z take I emanates from it out that way, not like that. Z take I goes out there. And its length has to be 2. So we start at 0, 1, and this vector, remember, is from I to the end of Z there. And that way it's going to be a detector, if you like, of the end of Z. And that's what we want. We're trying to find the locus, or where would you look for Z, the locus of Z. Okay, so can you see, if it's 2, then this is going to be forming a circle there, all positions Z take I, which have a length of 2. So the locus will be the circumference of a circle, centre, 0, 1, I, centre 0, 1, and radius 2. Do you get it? Okay, so when you draw these diagrams, I want you also to make this comment. So if your diagram's a bit wonky, not clear, then it can still explain what you meant by your diagram. So this is what it looks like down here. This is the possible, these are the possible, the whole circle, not just these individual ones, possible positions of Z, given the statement the length of Z take I is 2. Do you get it? It's quite intricate, isn't it? But see, Z is sort of come from the origin, but the centre of the circle is actually here at 0, 1, because these are different lengths of Z. Z can be different lengths as long as the distance of Z from I is 2. All right, think about that. Interesting stuff. Okay, come down now and let's check it algebraically. So we were just doing it geometrically. So if we're given this statement, let's let Z equal x plus iy, which we often do in proofs. So it's the size of Z take I, and then this is x plus collecting up the imaginary parts, I outside of y take 1, factorising that. Now we want the length of the vector, and remember here's the rule here. The length of vector a plus bi is square root of the real part squared plus imaginary part squared. So we're going to do it here. Root of x squared plus y take 1 squared. And we've got this. Do you recognise that as a circle 0, 1 with radius root 4 at 2 units? I'm not sure. So let's do a bit of revision of that for you. If you go back to the unit circle in circular functions, there's a few things we did with that. We said, well, there, that's 1 unit circle, and this is x and y. So by Pythagoras in that triangle, we said the square on the hypotenuse is the square, sum of the squares on the other two sides, by Pythagoras. Okay, oh, that's the simplest equation of a circle, isn't it? Here, the centre is the origin, 0, 0, and the radius is 1. And just as an aside here, just remember this is a theme or a crosslink in the course. We said this was cos theta, sine theta in circular function land, if that was theta. So as a result, we got the identity cos squared theta plus sine squared theta equals 1. So that was an interesting aside. But what I want to do here is to say that is the equation of the simplest circle there, centre, the origin 0, 0, radius 1. Now, do you know the idea of translations? I think you've had this earlier in your course. I don't know whether you could prove this, the transformation equations, but if y equals f of x is translated under a translation of AB, it becomes y equals f of x take a plus b, those constants, or y take b equals f of x take a. Can you see where the constants appear here in this general transformation equation? So let's do it for x squared plus y squared equals 1. Okay, if we transform this a, b, translate it, that's a transformation, becomes x take a squared plus y take b squared equals 1 squared. I call that 1 squared there. Okay, and from that, of course, you can see if this was R, the general form for the equation of a circle is this. Okay, so that's what we're using. So there's a little bit of maths for you to help you check these algebraically, because we want to do this. We want to have all maths to the rescue here to find that locus of z. Like, where must z lie if we know this information? Okay, so a couple of ways of doing it. So study this page very carefully. Go back, rewind it, and let me show you again. Let's go on and do some. Okay, so here we are. Here's some exercises. Consider the equation length of z equals 1. Now, I want you to try doing this in mixed ways, as the text has said here, and these screen clippings are from Hayes and Harris publications, so it would be good to have that book there. Okay, so have a look at some of these down here. The real part of z greater than 0, the size of z less than or equal to 2. Okay, see if you can picture them geometrically, and then there is one algebraic one here. All right, pause the presentation, have a go. I'll show you the answers now. Come down. Okay, here's some diagrams. It's important to get these right, though. Watch the algebraic one there, that's good. But over in the diagrams, could you please note that this is a dashed line around the circle? We must be particular here, because that value of 1 is not included. Okay, and we want the internal part of the circle in there, the internal part. Here we want the external part, but there's no equals 1, so that's got to be a dashed line where the size of the complex number equals 1. And over here, oh, this is interesting, the real part greater than 0, so that's got to be greater than 0, so that's a dashed axis, dashed line for the axis. It's got to be less than 2 or equal to 2, so that's a continuous line. That can be included. And this is a dashed line here because it doesn't include 2. Here it doesn't include anything on the left-hand side, because the real part has to be greater than 0, which is going that way. Do you get it? What about these? These are equalities, so the whole circle there is continuous, and this circle inside is continuous, because you can have the two boundary conditions, equality there and there. All right, interesting, isn't it? Be particular, be fussy about this, be precise, in other words, about your diagrams, given the nature of the inequalities. Okay, let's go on, let's do some more, and here's an example here. Illustrate the size of z take 2 is 3. Like, where would you look for z if you were told that? And you then use an algebraic argument. Okay, so from what we've said before, this is the distance of z. The distance from z to 2 is always 3 units. But what's the Z take 2? The distance from Z to 2, but we're going to look at the other way. We're going to take, because that's not right there, it's got to be up here. Okay, Z take 2 is going that way. So that's going to give us our tool. Because when we read this, Z to 2, we say if we go to 2 and then swing such that Z take 2 is always 3, this will be the centre of the circle, and all the points which are any points on this circumference will be 3 units from 2. So it's important to get the idea that Z take 2 is emanating from 2 north, coming out here, coming out from 2 north in various positions around there, because it's going to be 3 units, and you know the definition of a circle is a set of points which are the same distance from the centre. Here 3 units. So that will allow us to plot possible Zs. The possible Zs, I'm messing this figure up badly, aren't I? The possible Zs, therefore, are any points going out from the origin. Notice that they will not be the same length as each other. Right? The only thing that's the same is the length of that Z take 2, that is, the length of the vector emanating from 2 out to the circumference. Okay, so you should say this as well. Right, make the verbal statement as well as your graph here. So your graph looks like that, with Z take 2 going that way, and then you have your locus, which is the set of points on the circumference of the circle. Okay, let's do it in algebra land. So let's do x plus yi. So this becomes x plus yi instead of z. Take 2 equals 0. Let's collect up the real parts. X take 2 and the imaginary part equals 3. Then using the idea of the size of modulus, or absolute value of complex number, is the root of real part squared plus imaginary part squared. Squaring both sides, we get this. And that you recognise as the equation of a circle, which has a centre translated 2. Remember, x take a, 2 in the x, nothing in the y. There's no change in the squared term there. And this is r squared. So it's 3 units. So you can check it algebraically. Let's just check, before I let you loose on some problems down here, I want you to make sure you know what we're saying. When we say z take a complex number w, or omega, whatever you want to call it, z take omega is equal to, let's say, something like a, what that implies, and it's got to be a minus here, doesn't it, for sum of vectors around a closed figure, remember where it came from, that implies z, hang on, I'll just do this differently, I don't want to confuse you. It means the length of the vector starting at omega and going to z has a length a units. Okay, and that's going to usually give us a circle. We're going to get some other variations later, but it must be the difference there, z take that. So if I have something like, the book doesn't explain this very well, if I have something like z take 2 plus I, I've got to be careful. I would like to consider implies this is z take 2 take I, don't I? I have to make sure my second complex number is subtracted. So watch out for that. It's minus the whole point from which the vector is emanating. So you have to take a neg 1 out of this. Please make sure that this result you understand perfectly as being the length of the vector z take w, starting at w and going to z there. Okay. Are you ready? Here's some for you. Now be precise with your diagrams. Precise. So what's the equal sign? Less than or equal to? Oh, there's a plus in there, that could be a problem. Not sure about this one, might play with that. And this doesn't have an equal sign. So how is that going to be represented in terms of the circumference of the circle? Will it be shaded or will it be continuous? So be careful here, be precise. What's the inequality sign? Has it got equality as well as the inequality? All right, pause the presentation, have a go. I think you perhaps have to flip forward and back of the presentation now to check your answers. Don't keep doing problems if you're not sure, or if you haven't checked the first one. You could be repeating an error. Okay, so come down and look at the solutions now. Okay, so here we are, 2 part A. This didn't come out very well, so I've shaded the inside of the circle there, and the circumference is included there. And C, it didn't come out. Just notice that this is a dashed line here. It's a dashed line. You can see why, because over here there's no equality there. Okay, just greater than. And down here we've got some here as well. Okay, so it hasn't come out very well from the screen clippings, so I've shaded it in red and just reminding you of the dashed lines there. Okay, so this axis, of course, is dashed as well. Okay, that's more visible. All right, how did you go? Might have to go back and check those carefully. This is a popular aspect of this course, the idea of understanding the geometry of complex numbers on the plane. Okay, let's move on and have a look at another example. It's not so much a circle now, and you can see this diagram is what I had on the first page. So illustrate this equality. So what Cartesian equation does its graph have? So let's do it in Cartesian form. So we're looking at the locus of Z. Where does Z lie, if that's true? And what we might do is have a look at it geometrically and using an algebraic argument. So what does this mean? This means the distance of Z from 2 is equal to its distance from 2i. Notice that tricky do in here. You can't work with plus 2i. That does not infer a distance between Z and 2i. It's got to be Z take. So it's Z take neg 2i. So let's go to these points. Distance from Z 2. So here's 2 naught out here. So the distance of Z from 2 is the same as it's from 2i. Okay, so we're looking for Z, and there's 2 naught, there's neg 2i. So its distance from Z is equidistant from 2 naught and naught neg 2. So where would that be? Well, it's going to bisect this angle here, isn't it? Okay, so this is the line where the distance of the 2 points would be equal. Okay, so Z's going to lie somewhere between the 2 there, and that is on this line here. And that's wrong, actually. Y equals x. It should be, this is y equals neg x, isn't it, going the other way? Y equals x is there. So y equals neg x. That should be. So here, to do that, we've said it lies on the perpendicular bisector of that line. So it's got to be right in the middle. Okay, so Z up here, equidistant from those 2, has to be the line bisecting that angle there for equidistant between those 2 points. So a little bit of geometry there. Okay, and they like this. This might be a bit hard if you're not sure of geometry from your Cartesian coordinate geometry work in earlier years. All right, do you get it? So we're away from circles now. So the locus of Z, where I would look for Z, is on the line y equals neg x, because it is the bisector of the angle between the 2 axes, and these points are both on the axes. All right. Now, what about doing it algebraically? Let's stick it in here and in here. Okay, so there it is. Now, collecting real parts, x take 2 plus yi. Always, that's important, isn't it? Imaginary number is a plus bi, if you like. And these are the real, this is the real part and the imaginary part. Always write in the same form. So instead of z, you've got x plus yi over here. Now collecting up the real parts, there's only 1. imaginary parts here. Let's get rid of that. This is y plus 2 lots of I. And now we're ready to find the modulus or size of the complex number. So it's the square root of real part squared plus imaginary part squared. Same over here. Squaring both sides, then subtracting x squared and y squared from both sides and simplifying it. Neg 4x equals 4y, y equals neg x. So that checks our geometric work from above. Okay, now some people will prefer to do the algebra. Some people would prefer just look at it geometrically. But you've got to do it the way they want you to do it. So if they ask geometrically, you've got to do it that way. If they ask algebraically, you've got to do it that way. Generally, there's not time to do it both ways unless they've asked you to do that. All right, come down and see what you can make of these down here now. Oops, I won't give you so much there. Let's just come up a bit. Okay. Okay, illustrate the following using geometric methods and check your answer using an algebraic argument. So it's quite a bit of work here. I want you to do all parts. This is a big emphasis in the course. What is the geometry around plotting complex numbers on a plane, on the Argand diagram? What is the geometry around that? And can you see the overlap with Cartesian coordinate geometry from junior maths? Okay, reflections, rotations, that sort of thing. Okay, and then here, same thing, show algebraically that, and then explain geometrically why the answer to A is true. So it's an interesting one. What's the geometry? Okay, you need to be aware of that. All right, have a go. I'll pause the presentation. I'll go down now and show you the answers. Okay. So there we have A and B of that first question there. It's nicely explained here, I think, pretty well. Go through that. And then C. C for that question, and D. Got all D on there. Okay. Just watch here things like this. Okay. Things like that dashed line. Why is that a dashed line? You might have a look at that. All right, down here now, let's have a look at, hang on, did I get all those in? Let's have a look here. A, B, C and D. Oh yes, but I didn't, yes, the answer to that is already given, that's okay. So let's go down, and if the answer is already given there and you can't see how they got it, might discuss that with classmates and with your teacher. Find algebraically the points x, y such that z equals x plus yi and the conjugate of z is neg I, z. Okay, so you're looking for points now that are satisfying both of those conditions. So what could you do? Algebraically as a clue, you'll go to x plus yi and here simplify this idea here. The conjugate of z is neg I z. So here's the conjugate of z, which is neg I by that. Therefore, we've got these two parts here. Now, I don't like the way they've done this because I've just said to you a minute ago we should have real and imaginary parts. So this should be y take I x, shouldn't it? And then equating real and imaginary parts, x equals y and y equals neg x, or neg y equals neg x. So x equals y and neg y equals neg x. So therefore y equals x. So P lies on the line y equals x. Alright, so just watch this up here. They've skipped that step. They've said equating real and imaginary parts, but in this format it would be easy to get confused because that's a real part first, neg x. So I think you should put this step here where you put real and then the imaginary afterwards, and then you've got an easier, safer method of equating the real and imaginary parts with the other side. All right, do you want to do some? Let's have a look and we'll finish up there. 6, 7, 8, 9. So you need to do these algebraically. a bit hard to actually to see what's going on just geometrically now with these products. You can't interpret products very easily like that. You can interpret, remember the basic idea, Z take omega size, that is A, is the one that you can interpret most easily as a circle, centre, omega, and radius A. Okay, so watch this one now. Theta is pi on 4. Do you understand theta as the argument of the complex number? So graph it and then use algebra here to check it. Okay, arguments pi on 2, so these are the angles. This is an interesting one. Okay, so you might check that. Both of these here are interesting. And then this one, there was an error in the book. It should be graph r equals theta, where r is the distance from O and theta is any angle from 0 to 2 pi. And I'll show you in a minute how to do that on the calculator. So the idea with this one is to start plotting it. So if r is equal to theta, let's take theta as naught, that's that point. So r is naught also. Then you might take theta as pi on 4. So pi on 4 is there. That's theta is pi on 4. So its radius has to be, the length of that line has to be also equal to pi on 4, which is approximately 3.142 on 4, which is approximately 0.8 or something, 0.78 or something. So that's the length of that line. See the idea? So you do this length as pi on 4 as well. Then you might take pi on 2. Okay, pi on 2 is there. So what will the length of that r be? So I'd like you to try plotting it by hand and see how far you can get. It's an interesting sketch. Okay, so let's come down and look at the solutions now. So here's 6a, b, c and d. Check this carefully with the algebra there. The x plus yi, this is quite popular in this course, this sort of question. And 7, 8, a, 1 and 2, we'll have a look at the rest of this in a minute. Okay. B and C. So just watch this over here. This is a dashed line, be precise, and there's a hole in it there. Can you explain why that there's a hole in it? Okay. All right. Might have to discuss that one with your teacher. Let's have a look at 9. And I've got some solutions there on the calculator as well. So here it should be from 0 to 2 pi. We scrubbed that out. So can you see how this is done? When the angle is pi on 2, that's the angle around there. This distance here, the radius, must be pi on 2. Pi on 2, of course, approximately 3.142 on 2, about 1.57. Okay, there. And so on. As you go around, the angle theta is pi there, around to this point. This should be the value neg pi, because the radius has to equal pi, which is approximately 3.142. So this will be the point neg pi. And then when it's 3 pi on 2, right around there, this distance should be 3 pi on 2. The r should be 3 pi on 2. Because it's in the negative direction, that's neg 3 pi on 2. So getting this snail whirl sort of idea. When you ride around one revolution, so let's just scrub some of this out then. When you're doing one revolution, theta is 2 pi, so the radius there should be 2 pi. It's in the positive direction, so that point's 2 pi. Okay, you want to do it on the calculator. I think this is important because we're going to do parametric equations again later on, but this is polar equations now. So what do you do? This is Casio 9860 Plus, great calculator. So choose graph mode here, and so you go into the function, their graph, you actually have to change the type of graph to this one. So hit type, and there you have the polar form r equals. Later on we'll be using parametric form in a later part of the course. So polar form r equals, you get this window. If you then select the variable x, it will put in theta, not x. Okay, so just go to the x button, it's down below here. And if you hit that x r theta, xt theta I think it is, so theta will just pop in there. Then you need to go to the view window. So this is shift F3 for view window. And you scroll right down, so this is scroll down to the bottom of the usual view window, and just check a decent y value, -5 to 5, so you've got enough space this way to see it. And then you're going to specify t theta minimum 0, t theta maximum 2 pi. Okay, so put 2 pi in there, it gives you that decimal equivalent, and then don't worry about the pitch here. It should be less than 0.1 though, so you're getting a nice plotting of points. And there's your graph on the calculator. So just be aware of this now, particularly this type here, the type of function you're plotting. Previous to this you would have used y equals f of x. Now we're going to use these two. At this time polar r equals, and later in the course parametric equations, and that's very interesting work. All right, what do you think? It's really exploded, hasn't it, this idea of complex numbers and plotting them. I hope you're enjoying this. Go back over it, build up some skills. That's important to be confident, and check and talk to others about the geometry of surrounding points on the plane there. Okay, cheers for now. I'll catch you a bit later.